In Chapter 9, we'll be continuing with hypothesis testing and also tying back in confidence intervals from Chapter 7. The difference in this chapter is that now we're working with 2 samples instead of a single sample. Now, the main thing that changes when we add in a second sample is the standard deviation. Recall that when we have a 1 sample test and it's categorical data, the standard deviation is radical PQ over N. Now we're dealing with 2 samples. Each has their own p-hat, and we have to combine them. So the way we do that is we take each one of these standard deviations and we square it. And when we square it, the square and that square root cancel out. We're left with just this fraction right here, outside of a square root. Same thing over here. Okay, now we're going to add those 2 fractions together and square root that sum. Okay, this is the basic premise for combining standard deviations in 2 categorical samples. It's a little different whether we're doing a hypothesis test or a confidence interval, but that's the overall method of combining our standard deviations. So in example 1, we're going to do a hypothesis test on nursing homes and what percent of them have resident vaccinations less than 80%. So we have 2 samples. One of those samples is of small nursing homes, and 12 out of 34 of them, 12 out of 34 had resident vaccinations less than 80%. Our second sample is of large nursing homes, and in this one we have 17 out of 24. So that's going to give us 2 different p-hats. It's telling us that the alpha level is 5%, and it wants us to test the claim that there's no difference. That's going to be useful in making our hypotheses. So for the parameters, instead of having just 1 parameter, now we have 2 different parameters. The first one is for small nursing homes. So we're going to say P sub S is the true proportion of small nursing homes with resident vaccinations less than 80%. And then PL is the proportion for large nursing homes. Hypotheses. The null hypothesis is always that the 2 proportions are the same. Okay, it's never anything different than that for null hypothesis. Alternative can be a less than sign, a greater than sign, or not equal to. We're testing no difference, okay, which means that we're going to use a not equal to sign for our alternative hypothesis. We could also write these hypotheses like these, where we just take each of these things and we subtract it to the other side. Okay, here we have a difference equal to 0, meaning they're the same. Here we have a difference that's not equal to 0, indicating that they're actually different proportions. Now we want to find the sample proportions and something called the pooled proportion. Sample proportions are easy enough. For small nursing homes, it was 12 out of 34, and for large nursing homes, it was 17 out of 24. So we got 0.353 and 0.708 for our sample proportions. This pooled proportion is based on the null hypothesis. Now remember, anytime we do a hypothesis test, we're always assuming that the null hypothesis is true. And in this case, the null hypothesis says that these 2 proportions are actually the same value, which means that any difference we see here in those samples is the result of natural sampling variation. Meaning if we were to open a package of M&Ms and find the percentage of blue M&Ms, okay, in one package it might be 17%, in another package it might be 22%, but in actuality it's just natural sampling variation. They all come from the same factory where 20% of M&Ms are blue. So if our null hypothesis is true, these are actually not different. It's just that our sample sizes are too small to actually show that they're the same. So what we're going to do is we're going to combine both of our samples. So we're going to take this one, combine it with that one, and just look at nursing homes in general. So if we're combining these and looking at all nursing homes, there were 29 out of 58 nursing homes that had a resident vaccination less than 80%. This is our pooled proportion, and that's what we're going to use to make our standard deviation. So for a hypothesis test, we don't keep our fractions separate. So we don't have the 12 out of 34 for one p-hat and 17 out of 24 for the next p-hat. Instead, we just combine them all together and we get this single p-hat for all nursing homes. The reason we do that is because the null hypothesis is saying that these 2 proportions are actually the same. So we find the standard deviation. We use that pooled p-hat in both of these fractions, and we put it over top of each of their sample sizes. So it looks like this, 0.5 times 0.5 over 34. That was the small nursing home sample size. And then same thing with 0.5 and 0.5 for the large nursing home. Okay, we get a standard deviation of 0.1333. We want to find a z-score for this. Okay, so now let's go back and look at our sample proportions again. So small nursing homes had 35%. Large nursing homes had a lot more, 71% about. Okay, there's a difference here of 0.355. Okay, it could be positive or negative depending on which way we subtract it. That's really not important. Okay, so when we find a z-score, we want to see how unlikely that difference would be. Okay, would it be unusual to see a difference of negative 0.355 based on this standard deviation that we just found? Okay, we subtract the null hypothesis, and that null hypothesis is always a 0 here, which means we really can just leave that part out and just look at, is that an unusual difference compared to that standard deviation? Okay, so we subtract them. This can be ignored. And we get a z-score of negative 2.66. So now we want to find a p-value. This difference of negative 0.355 was 2.66 standard deviations below the mean. We're just going to look up that z-score in our z-table, and keep in mind that this is a two-tailed test. So whatever we have on this side of the curve is also going to be on the other side. Okay, when we look this up, we get a p-value of 0.0039, and because it's also on this side, we have to double it. So 2 times that gives us our actual p-value for the full test, 0.0078. That's going to lead us to reject the null hypothesis because that p-value is smaller than the 5% significance level. And we write our conclusion. The conclusion is still always about that alternative hypothesis. In this case, there's sufficient evidence to suggest there's a difference in the true proportion of small and large nursing homes with a resident vaccination rate less than 80%. So that was a hypothesis test. Now let's tie in confidence intervals, which we last did in Chapter 7 with one sample. The problem is the same with one key difference, and that's the wording at the end. Here it's asking us to estimate the difference. That's what's telling us we need to do a confidence interval for this problem and not a hypothesis test. If it were a hypothesis test, it would be a yes or no question where we're evaluating a claim or a hypothesis. So part A, define the parameters. These are the same as last time. And part B, we did in the hypothesis test find the sample proportions. Okay, we got 0.353 for the small nursing homes, 0.708 for the large nursing homes. And we're going to estimate the difference between these two. So we're going to want to subtract them. And while it isn't important which one we put first, right now, when we get to our final conclusion, it is going to be important which one comes first. So just note that we have small nursing homes first, large nursing homes second. Now we want to find the standard deviation, and I had mentioned on one of the earlier slides that the standard deviation for a confidence interval is a bit different than the standard deviation for a hypothesis test. When we just did the hypothesis test, we pooled both samples to make one large sample. We called it the pooled p-hat or p-bar, and we used that in both fractions in our standard deviation calculation. We're not going to do that with confidence intervals. The reason we did it for the hypothesis test is because we had that null hypothesis that said these two proportions are actually the same. The difference is 0. They're not different at all, in other words. The entire hypothesis test is based on that being true, so that's why we put those two proportions together. In a confidence interval, we don't have that null hypothesis saying that they're the same. In fact, the wording is saying estimate the difference. We're acknowledging that these two p-hats are different. So when we do our confidence interval, we want to keep our two fractions separate. We have our fraction for the small and our fraction for the large, and it's using the actual p-hats from each of those samples. Okay, so here's the small sample. 0.353 is the p-hat. The q-hat is just 1 minus that. And when we do the large one, we're using 0.708. Okay, we get a standard deviation that's slightly different this time, 0.124 compared to 0.1333 when we did it last time. Critical value for a 95% confidence interval. Remember, when we do a confidence interval, it's talking about the center of our normal distribution. 95% is cut out of the middle. That leaves half of the leftover on both of these sides. We're going to look up 2.5% in our z-table, and we get our critical value 1.96. Margin of error is just this z-score times our standard deviation, 0.243. Part F, write the actual interval. We always start the interval with a point estimate. It's what we're trying to estimate, which in this case is the difference between these two population proportions. So we have our two samples, And if we subtract them, we get negative 0.355. That's going to go up here in our point estimate. Add and subtract the margin of error, which we just found on the last slide, 0.243. Okay, when we add and subtract those, we get our actual interval, negative 0.598 to negative 0.112. Keep in mind these are percentages, so it's negative 59.8% and negative 11.2%. Part G. I had mentioned on a previous slide that the order here is important, and this is where that comes into play. This is what our answer is going to look like. We are 95% confident that the true proportion of small nursing homes with resident vaccinations below 80% is between 59.8% and 11.2% lower than the true proportion of large nursing homes. So here's how we craft this answer. First off, this word lower is because both of these are negative. It would be higher if they were positive. What this is saying is we have P hat S first. So we had small nursing homes first when we did our point estimate up here. Okay, our interval is telling us that this first thing is between 59.8% and 11.2% lower because of those negative signs than the thing that came second. If we had done this in the opposite direction and put PL first and this one second, we would have had a plus sign here. Would have been a positive 0.355. Both these signs would have been switched, but now large would have come first, small would have come second, and we'd be saying that large is between 11.2% and 59.8% higher than small. Okay, so it would be saying the same thing, just the wording slightly changes. Key thing is that we keep the order here. Small comes first, large comes second. The interval is telling us what the difference between those two things is. Part H, based on that interval, can we conclude that there's a difference in the true proportions? We can, and the reason we can is because 0 is not in this interval. Okay, keep in mind that anytime we do a two-sample test, it's going to be about the difference between them. If there's a 0 in there, it's saying it's possible that there is no difference. It's possible that the difference is 0%. So in other words, they're actually the same. 0 is not in this interval. All these values are below 0. So our answer is yes. Okay, the interval is about the difference in proportions. A difference of 0 would suggest it's possible that the proportions are actually the same. Since the interval does not include 0, there's a statistically significant difference in the true proportions. This is really the only thing you need to write to answer that question. The rest is just explaining it.